Hi, welcome to the binomial distribution. In this video, we're going to derive the binomial distribution. Let's say you flip a coin 12 times. What is the probability that it comes up heads 7 of those times? Or let's say you randomly draw a card out of a standard deck, look at it, replace it, and shuffle the deck. If you do this 4 times, what is the probability that 2 of the times you drew a card, you got an ace? Or perhaps you and your 2 housemates draw straws to determine who has to vacuum the floor. If you do this 7 times, what's the probability that you have to vacuum the floor 4 times? The answer to questions like these is the binomial distribution. Additionally, the binomial distribution is also important for understanding Poisson and Gaussian statistics. In fact, if you watched the Poisson distribution, Derivation, on this channel, you've already seen the binomial distribution, although we didn't point it out. We will use a couple of handy results from combinatorics, which are presented in the short video, A Tiny Bit of Combinatorics. If you know what a factorial is and how to derive this expression, n choose m equals n factorial over m factorial n minus m factorial, then you're probably fine to jump in here. If not, you might want to check out that video first. We'll derive the binomial distribution by doing a thought experiment involving flipping a coin. First, let's review the basics of coin flipping. When we flip a coin, it has a certain probability of landing head side up, that probability would be pH, and a certain probability of landing tails side up, that probability would be pt. These two probabilities add up to 1 if the probabilities are expressed as fractions, or to 100% if the probabilities are expressed as percents. So here we have an example where pH, the probability to come up heads, is 0.4 or 40%, and pt, the probability to come up tails, is 0.6 or 60%. We take every flip of the coin to be independent, meaning that every flip has the same probability pH of coming up heads and the same probability pt of coming up tails. So whether a coin has come up heads 5 times in a row or came up tails 3 of the last 7 flips, the probability for the next flip to come up heads is still pH, and the probability for it to come up tails is still pt. So to get the probability of a sequence, here for example, heads, tails, heads, heads, etc., we multiply together a factor of pH for every flip coming up heads and a factor of pt for every flip coming up tails. So here we would get pH, pt, pH, pH, etc. Note that the order of the sequence doesn't affect the probability. Only the numbers of flips that come up heads and tails are important. So if we flip a coin 10 times, the 3 sequences shown here all have the same probability, pH to the 5th, pt to the 5th, because all 3 sequences include 5 flips that came up heads and 5 flips that came up tails. Let's take a coin with a probability pH of coming up heads and a probability pt, which equals 1 minus pH, of coming up tails, and flip it n times. What is the probability that it comes up heads exactly m, where m is less than n, times, and tails exactly n minus m times? The answer to this question is the binomial distribution. Note that we are only interested in the number of flips that come up heads and the number that come up tails, not in the order in which they happen. There can be many sequences of flips where m flips come up heads and n minus m come up tails. We want to include all of these possibilities. First, let's get the probability of a specific sequence, here shown as heads, tails, heads, heads, etc. We saw before that we get a factor pH for each flip that comes up heads and a factor pt for each flip that comes up tails. So here we would get pH, pt, pH, pH, etc. So if m flips come up heads, we get m factors of pH and n minus m factors of pt. Therefore, for a given sequence of n flips, where m come up heads and n minus m come up tails, the probability is pH to the m, pt to the n minus m. and that equals pH to the m times 1 minus pH to the n minus m, because pt is equal to 1 minus pH. This is the probability of any one sequence where m flips come up heads and n minus m flips come up tails. But what we want is the probability for m flips to come up heads and n minus m to come up tails. So we have to consider all possible sequences which have m flips come up heads and n minus m come up tails. For example, for n equals 3, m equals 1, we want the probability to get any of the following: heads, tails, tails, or tails, heads, tails, or tails, tails, heads. Every sequence with m flips coming up heads and n minus m flips coming up tails has the same probability. But we still need to know how many sequences of n flips contain m heads and n minus m tails. In other words, out of n flips, we need to know how many ways there are that exactly m come up heads. To do this, we're going to reference a result derived in the video, a tiny bit of combinatorics. In that video, we saw that the number of ways to choose m out of n objects, disregarding the order in which they are chosen, is what is called n choose m, which equals n factorial over m factorial n minus m factorial. If this result is unclear, you might want to check out that video. So the probability of n flips of the coin yielding m heads and n minus m tails is something that we'll call p of m, which takes two parameters, p sub h and n, and that's equal to ph raised to the m power times 1 minus ph raised to the n minus m power multiplied by n factorial over m factorial n minus m factorial. Now this expression is the binomial distribution. Let's look at this distribution for different values of n and pH. So first, let's look at the case of a fair coin, where pH equals pt equals 0.5. Here we've plotted the binomial distribution for n equals 10 and n equals 20. In both cases, you can see that the distributions are peaked at m equals pH times n, which in this case is equal to n over 2. For the case where pH times n is an integer, the binomial distribution will be peaked at pH times n. If pH times n is not an integer, then the distribution will not be peaked at exactly pH times n, but it will be close. And now let's look at the case where pH is equal to 0.4 and pt is equal to 0.6. Here we've plotted the binomial distribution for n equals 5, n equals 10, and n equals 20. In all cases, you can again see that the distributions are peaked at pH times n, which in this case is equal to 0.4 times n. You can also see that in this case, unlike the previous case where pH and pt were both equal to 0.5, that there's a noticeable asymmetry in the distributions. Also, the asymmetry gets smaller as you go to larger n. So here we can compare the case where n equals 5 to the case where n equals 20, and we can see that the distribution for n equals 20 appears more symmetric. Let's make one last note about the practicalities of using the binomial distribution. Here we have seen that for n flips of the coin, the probability for m of the flips to come up heads and n minus m to come up tails is pH to the m times 1 minus pH raised to the n minus m power times n factorial over m factorial n minus m factorial. Now, this expression is exact. However, in certain large n limits, it can be approximated by other distributions, such as the Poisson or Gaussian distributions. When appropriate, we usually use these other distributions because the large factorials are inconvenient to work with. We'll discuss these limits of the binomial distribution in other videos.